So there are things that we will teach you in this first year that'll be all and end all of a particular topic. And there are other areas in which we're just going to give you kind of a glossy introduction. Hope we're not lying to you too much, and give you the foundation that you can then build on in future modules. And quantum chemistry is very, very definitely one of those types of areas. It's really tough to get. You need to be really good at maths in order to understand it fully. It is extremely satisfying when you understand it, but you are going to have to be patient and not get frustrated with it. The way that we're doing it is effectively analogous to peeling an onion from the other direction. In other words, instead of starting from something and uncovering each layer until you get to the center, we're going to start at the center and kind of build up from there, hopefully clothe it up from there. Anyway, so it follows quite nicely from our discussion of hydrogen spectra. If you remember to the last movie, based on observable spectra, always important in science that you have observations from which you are going to develop your theories, that the best way to explain it was to say that electrons in a hydrogen atom, or an electron in a hydrogen atom, electrons in hydrogen atoms, are only allowed to be in certain orbits with associated certain energies. And the spectra that we see, which are very limited in the number of energies affected, are simply where electrons are either moving up in energy from one allowed orbit to another, or moving down in energy from one allowed orbit to another. It explains quite nicely all those spectra that you see. Big trouble is, it only works for one electron. So it works for hydrogen. You can get that beautiful little explanation of the frequency is equal to the Rydberg constant times 1 over m1 squared minus 1 over m2 squared. It works well for He plus, just with different values of the constant. It works well for Li2 plus with different values of the constant. However, it doesn't work as soon as you have more than one electron in there. Things like helium and so on still have spectra, but you can't get a cute little expression that relates all of the absorbed frequencies, the absorbed energies, and so on for those. Even with that, though, while it works for one electron, does it really make sense? And the answer is not really. I mean, let's face it, if you think of it in terms of particles, you've got a negative particle going around outside a positive particle. First of all, doesn't a negative particle just go on and get attached to the positive party? They attract each other. Secondly, of course, why would a particle be limited to certain positions, be limited to certain energies? And the answer is it really doesn't make sense. So how do we explain it? And the way that it's explained is through quantum chemistry. The idea of quantum chemistry really stems from the ideas that everything has wave-particle duality. That was used for light. Einstein explained the behavior of light in terms of wave-particle duality. De Broglie took that idea and said that everything has some wave properties. I can look at everything and I can generate a wavelength for it. So I have a wavelength. Don't laugh at me because you have a wavelength. Thing is, though, for observable particles, that wavelength, those wave properties really are virtually negligible. However, as a particle, in quotes, gets smaller and smaller and smaller, that wavelength becomes more and more and more significant. And the little equation here, wavelength, the de Broglie wavelength, is h. H, if you remember, 6.626 times 10 to the minus 34 joule seconds divided by the mass times the velocity. So something has to have a pretty small mass in order to make this a significant number. So a big fat lump like me, my wavelength is so tiny it's pretty much negligible. You go down to a tiny little thing like an electron and its wavelength becomes very significant. So what we're saying here, thanks to de Broglie, is that in order to explain the properties of electrons, we cannot just think about it in terms of particles. We have to ascribe to it a certain amount of wave property. And when we do that, things do become a bit more sensible. Waves have got very distinct positions. Waves have got very distinct energies and so on. Okay. In order to add to that as well, a chap called Heisenberg, Heisenberg's uncertainty principle, of course, something that's made it into the consciousness of the general population. But essentially what Heisenberg said is you can't know the position and the momentum or the energy of a particle simultaneously. Now we can actually think about this on the macroscopic level. think about taking a picture at a football game, and the ball has been kicked and it is soaring towards the goal, and the goalkeeper is making a big dive for it and so on, right? Well, if you take a picture of that, you can get a very sharp image of where the ball is, where the goalie is, and so on. Okay, so you can know their position there macroscopically because you can see them. But what was their momentum as they were doing that? How fast was that ball going? How fast was the goalie desperately leaping to try and catch it, and so on? And the answer is, if you know the position perfectly, you have no clue about the velocity and so on. On the other hand, if you take a slightly scummier picture with a cheaper camera, then the ball is going to be somewhat blurred. Well, in that case, you can, knowing what the frame speed is, for example, of your camera, you can get a feeling, get a measurement of the velocity of the ball and the velocity of the goalie from that blurring, but because it's blurred, you can't know the position simultaneously. Somewhat better analogy would just be, think about me walking around the classroom. I know that's a horrible image, but keep it there for a little while. If I'm walking around the classroom, you can measure my velocity, but of course in measuring my velocity, as you're doing it, my position is changing, so you can't know my velocity and thus my momentum at the same time as my position. What's the only way you can get my position exactly? Well, you just stop me. However, if I'm stopped, you don't know what my velocity was. The very act of measuring disturbed the other one. Okay, now you imagine how hard it is to do that macroscopically. Now you go down to things you can't see that have these wave properties as well, like electrons. So the Heisenberg uncertainty principle is very, very important. You cannot know the position and momentum simultaneously. Little mathematical equation for this that I'm only putting in so that I can give you a couple of calculations to do in the homework, but it is something you need to have seen, and that is that the uncertainty in the momentum times the uncertainty in the position has to be greater than this number here. Now this is a pretty small number, again, that's good old h, right? 6.626 times 10 to the minus 34. But it's still not zero. There is that uncertainty. And of course, remember, when we are dealing with these teeny little things, h actually is not that small, relatively speaking to those. Something that physical chemists will do a lot, I'm not quite sure why they do it, I think it's just because they're lazy, is instead of writing out h over 2 pi, which happens a lot, they write h with this little bar through it. So h with the bar divided by 2 is actually h over 2 pi divided by 2, which is h over 4 pi. It's a silly little thing. But you see h with a line through it, it's just h over 2 pi. Anyway, how does this help us in our argument now? Well, we got those atomic spectra, so we can determine energies. And if we know the energy, we can only determine the probable position of the electron. We can't know where the electron's going to be. We can't put it in an orbit because that would be saying, hey, we know where that electron is. So instead of talking about orbits from now on, we're going to talk about orbitals. And orbitals are effectively the probable position of an electron. Now we'll get more detailed with that explanation as we go through the movie, but I want to make sure you have that right from the start. So I said Heisenberg had reached the consciousness of the general populace. And worse than that is Schrödinger, right? Everybody who considers themselves to be educated, or at least pseudo-educated, knows about Schrödinger's equation, and you'll see these snotty gits, particularly at historians and English professors' party, going on about Schrödinger's cat, ha ha ha, like they have a clue what Schrödinger was going on about. But anyway, what Schrödinger was going on about was the fundamental way in which we apply maths in order to explain and understand atomic structure. And the fundamental form of the Schrödinger equation is this. Now, it looks pretty harmless, doesn't it, right now? I mean, yeah, a little bit weird. Why do you have that cap on the H, and why do you have these Greek letters in there, and so on? But it does look fairly harmless. Schrödinger's equation is the fundamental equation of things that people have spent literally millions of hours and millions of pounds worth of computer time and so on trying to unravel and apply. And you'll touch on that a little bit here, more so in the quantum part of your Structure and Bonding 2 module in the second semester. And then in the second year, we have a thrilling module, Computational Theoretical Chemistry, that will be basically, essentially around, let's solve the Schrödinger equation, or get as close as we can to it. You can only solve it exactly for one electron systems, but you can get approximate solutions to this that will help you significantly understand atomic and molecular properties. Anyway, what are these things? H with a cap is called a Hamiltonian. It's a maths operator. Essentially, it's just a list of instructions, and I'll give you a very simple operator in a minute. E is that energy that we know. We know from spectra the energy differences, so we can get a clue about the energies of the particular energy levels. So those we know. And then this psi n, right, is a so-called wave function that corresponds to the nth energy level. In other words, what the Schrödinger equation allows us to do is it allows us to take these energies that we've got and generate from that this wave function that describes the electron that has that particular energy. And now, a wave function is a very complex concept, while at the same time a very easy concept if you don't allow it to be too difficult. A wave function is just where we try to describe the electron by a mathematical function. Now, some of these mathematical functions get really disgusting looking, and of course, as I said, unless you just got one electron in there, then it's going to be approximate anyway. But a wave function is just a maths function. Okay, x squared could be a wave function. It's not that easy. Cosine of x could be a wave function. That's a bit closer, but it's still not that easy. But it's a mathematical function. Okay, and you can get every property of the particle you could ever want if you know the wave function of the electron associated with a particular energy. Okay, now the wave function, I'm going to throw this at you. It's not that big a deal, but you need to have seen it. It's finite, it's single valued, it's continuous, its slope is continuous, and it can be plotted on a graph. Okay, might be a really big graph, might be a really weird looking picture, but you can plot these mathematical functions that describe the particle on a graph. Just to give you a couple of quick, silly little things, okay? Before I do that, I'm going to introduce two other little words, okay? The wave function is an eigenfunction, and the energy is a so-called eigenvalue. Now, what that means is here we've got a function, okay? Could be really complicated, could be really simple. You're going to see a really, really simple one in a minute. But if we take that function and we do something to it, right? We apply these operations, then we will end up, if this is an eigenfunction, okay, we will end up with that same function just multiplied by a number, that eigenvalue. Okay, you'll see this several other times, but I just want to throw those words out at you and use them to illustrate this whole idea. So let's keep a nice and simple operator. Multiply by 3 and add 6. And let's say that we can only think in terms of whole numbers. Okay, so here is a fancy way of our operator. When the operator acts upon whatever function we have, we're going to multiply that function by 3 and we're going to add 6 to it. Okay, now what if that function was 2? Okay, so we'd say 2 multiplied by 3, add 6, and that is 12. Okay, so when we have taken this function 2, 2's a function, okay? When we've taken that function 2 and we have applied the operator on it, we get 12. Now 12 is of course 6 times the original function 2, okay? So what we'll see in a second is we can say that 2 is an eigenfunction of this operator and its eigenvalue is 6. Okay, and the way we say that is because we took the operator, we operated on 2, and we got back 2 times the number. On the other hand, how about 5? All right, if we take 5 and we do this operation on it, well, 3 times 5 is 15 plus 6 is 21. That is not a whole number times 5. So thus, 2 is an eigenfunction of this operator, and its eigenvalue is 6. 5, on the other hand, is not an eigenfunction of the operator. Okay, we have these operators, these really long, complicated operations, series of mathematical instructions. Our wave functions are such that when we apply this mathematical operation to that wave function, we'll get the wave function back times a number, and that number will be the energy that we can get from the particular spectra. This obviously is a bit easy, just to make you quake in your boots. Let's talk about something a bit closer to reality. A typical simplistic Hamiltonian might look something like this. Now, this is just saying do some differential calculus. Some of you have had A-level, some of you haven't. You will have about differential calculus later on. Do some differential calculations on it twice, okay? And a typical wave function might be something not even cosine 2x, but cos 2x is a little bit closer to it. So if we take cos 2x and we differentiate it twice, then we actually get minus 4 times cosine of 2x. So hopefully you can see here, this was our wave function. We've done this operator on it. We've got that wave function back again times minus 4. Minus 4 is the eigenvalue, and cosine 2x is an eigenfunction of that operator. Does that sort of make sense to you? Just to really sort of throw it at you, let's get even nastier, shall we? And let's throw out a couple of real operators. Okay, for momentum in one dimension, if we're interested in determining the momentum of our particle, we take our wavelength and we would apply this operator to it. And this is just in the x direction. And the eigenvalue we'd get out would be the momentum. Okay, it looks pretty gross, doesn't it? Don't stress about it now. Just agree with me, it looks gross. Kinetic energy is even grosser, okay? If I wanted to know the kinetic energy of the particle in one dimension, I would take my wave function, I would apply this operator to it, I'd get back the wave function multiplied by the kinetic energy of the particle. If I generally analyze space from the wave function, okay, then what I would get back is I would get various equations associated with 3 quantum numbers. And these quantum numbers are limited because of the energy limitations, right? Remember, going all the way back, electrons can only have certain numbers of energies. We had orbits that corresponded to those energies. Now we're talking about having orbitals that correspond to those energies. Orbitals are not saying, hey, the electron is absolutely here, just as we'll see in a little bit. It's probably going to be here. And those orbitals are described by 3 quantum numbers that are part of the whole wave function and Schrödinger equation solution. I'll remind you, we've seen that phrase quantum number before, going back to the orbit explanation of atomic structure. Each orbit had a number, the n equals 1, the n equals 2, the n equals 3, that was associated with that energy of it. Remember, the energy of the orbital was minus 2.18 times 10 to the minus 18 times 1 over n squared. That quantum number led into the energy. Well, the 3 quantum numbers that we get from our Schrödinger equation and the wave function lead into describing that orbital. Okay? Now, at this point, I could go 2 ways in this movie. What I'm going to do is I'm going to sort of take the next 3 slides in which we're going to take you to where I want you to be in terms of knowledge that we're going to apply in the next sequence of stuff. But then we're going to backtrack a little bit, effectively come back to this slide here and go in a slightly different direction, getting more detailed about our orbitals and about the wave functions. But what we're really interested in for now, the quantum numbers. And the quantum numbers describe the properties of the orbital. And we have 3 right now quantum numbers that we're interested in. So-called n quantum number, known as the principal quantum number. This relates to the size and the energy. And it's the same conceptually as the quantum number we saw back talking about the hydrogen atom. This describes the so-called shell. I know that word shell is familiar to you from your A-level. We will use shells a lot. They relate back to that whole hydrogen atom explanation. It's a nice way to describe it. It's a nice simplistic view that enables us to address other properties of atoms without getting too complicated. N is limited. It has to be a positive whole number. Lowest one is 1, then 2, then 3, and so on. Highest we go in our practical chemistry is 7. Now, another quantum number is L. Okay, a little script L just to make it clear it's L rather than anything else. This is known as the angular or the azimuthal quantum number, and this is related to the shape of the particular orbital, and as we'll see, it also has an effect on the energy of the orbital. We call this the subshell, and I know again you're familiar with the word subshell. Now, the number of values that L can have is limited by the value of n. L can go from 0 to n minus 1. So if we look at this little chart here, if n is 1, L has to be 0, end of discussion. If on the other hand n is 2, so that's a bigger distance away from the nucleus on average, they're spaced to have 2 subshells. L is 0 or L is 1. N is 3, going all the way back to the orbit model, that's even further away from the nucleus. There's space for 3 subshells, 0, 1 or 2. If N is 4, there's 4 subshells, and so on. We're only actually chemically interested in L being 0, 1, 2 or 3. Now the last quantum number we're interested in right now is M, or sometimes you'll see it M subscript L. This is the magnetic quantum number. This tells us about the orientation of the particular orbital. It's actually what helps us define the orbital. To define any particular orbital, we need the 3 N, L, and M. And again, the values of M are limited by the values of L. M can only go from negative L to positive L. So if we look at this chart here, if N is 1, L had to be 0. If L is 0, M has to be 0. But on the other hand, N is 2, L could be 0 or 1. If L is 0, M has to be 0. On the other hand, if L is 1, M can go from negative 1 to positive 1. So it could be negative 1 or 0 or positive 1. Continuing on, I won't get silly with it, but just think about N is 4. If N is 4, L could be 0. In which case M is 0, or L could be 1, in which case M could be minus 1, 0, or 1. L could be 2, in which case M could be minus 2, minus 1, 0, 1, or 2, and M could be 3, in which case minus 3, minus 2, minus 1, 0, 1, 2, 3. Okay? In other words, if ML is the orbital, in the first shell, there's only 1 orbital. In the second shell, there's 4 possible orbitals. In the third shell, there are 18 possible orbitals. And in the fourth shell, there are 16 possible orbitals. And we'll see those numbers repeated in our next movie as we start really talking about the periodic table. We can relate the L value to orbital shapes. And I want you to be very familiar with these pictures. If L is 0, we call it an S subshell. M, of course, had to be 0. And the shape of such an orbital is a sphere. If L is 1, it's a P subshell. That is 1, then M can be negative 1, 0, or positive 1. And the shapes of the orbitals described by this, sometimes called a dumbbell, you can have them. There's 3 possible values of M, so that's 3 orbitals, one aligned along the x-axis, call it px, one on the y-axis, call it py, one on the z-axis, which will go in and out in this way, we'll call it pz. And just to show you where it lies, I've sort of rotated it round a bit so that now y would be coming out as z going vertical, x still horizontally. So that's this orbital flipped by 90 degrees. If L is 2, we call it a d subshell. Remember, there's 5 possible M values, so 5 possible orbitals. 4 of them have this 4-leaf clover shape. This one here looks like a P that's got a little belt round it. Second year, you'll worry about why this one is weird compared to these other ones. But right now, I just want you to know their shapes of them. If L is 3, it's an F subshell. 7 possible values. I'm not good enough on the computer to draw them. But at least earlier this year, there was a really nice little link there that you can go to get the pictures of those. I do expect you to be familiar with the pictures of F, but to know the pictures of S, P, and D very, very, very well. And then all of these orbitals can go into an energy level diagram. And right now, for just the hydrogen atom, we would say you've got the original shells, the orbits. But now we say that we split those into subshells. So N is 1, has 1 subshell, which we would call the 1s. Okay, the 1 comes from the first shell. It's an S because L is 0, so it's a 1s. N is 2, you've got the 2s and the 2p. The p comes from L equals 1. N equals 3, 3s, 3p, 3d. And N equals 4, 4s, 4p, 4d, 4f. Okay, the number corresponds to the shell from which they came. The letter is associated with the subshell and the shape of the orbitals. And talking of orbitals, this is where it can get really complicated. N equals 1 first shell, there's 1 subshell, it's an S, there's only 1 orbital in an S subshell. Go up to the second shell, there are 3 orbitals in a P subshell, and of course the second shell can have the 2s or the 2p. Third, we've got 1 orbital that comes from the S subshell, 3 orbitals that come from the P subshell, 5 orbitals that come from the D subshell, and then I run out of space on the 4th one, so I'm just going to put in there are 7 F orbitals. Okay, 25 minutes, a bit longer than I would normally like, but I'm going to pause here and then go into our second part of this movie. And all we're doing here is just going back to that previous concept, and instead of just jumping into quantum numbers, we're actually going to have a closer look at the wave function.